morning and welcome. As Hayden says, my name is Chris Jones. I'm the Field Applications Engineer for Secure Thingz. I've been in FA quite a few years now, and one of the things we want to talk to you about today is bringing security into the real world. I think explaining how you actually deploy security on real-world, embedded products, the actual MCUs. So I want to look at how that's actually done. So one of the things I want to talk to you about, and hopefully you'll take away from this today, is the importance of a chain of trust. And also how software can be protected against using development tools that leverage this chain of trust. So it's key to have this chain of trust, which is usually anchored, or must be anchored by a root of trust, and how we can grow from that to embed security, not only in the product itself, but through its life cycle. So I've got a lot of subjects here. Don't be too scared. It just shows each slide. So I'm going to cover all the different areas, the actual flow process itself that I'll take you through, the different aspects of trust anchors and the root of trust, and then you've heard in the keynotes about identity, and it's how important it really is. Talk about some of the details of what you need on the actual hardware, the microcontrollers themselves. And this is where the semiconductor guys are really stepping up to the plate and improving the security actually on the bare metal products. And you'll see a lot of that coming out early next year. And then look at some of the actual processes of deploying your security, so the provisioning and the mastering of your software images. So this is kind of the flow I want to talk about in this session. And it's basically targeted at those guys who are actually designing and developing an IoT product, and the things you need to look at. So one of the things before you start out is these are the important things you need to identify. And the first thing is, what trust anchors are going to be available to you in your software development? How can I put my trust anchor into this device that I'm actually going to use in my IoT product? So we're looking at the supporting the formation of identity into the product, and then ultimately creating this root of trust. What do I need to create this truly identity, and that I can completely trust throughout the rest of the chain? And then, of course, that links in very closely with some sort of public key infrastructure that you want to implement in your product. And that's basically the design side of it. So once you've designed that product, sometimes I think designers forget, okay, I've designed it, it's really secure, I've put in this really cool secure system, I'm using a PK infrastructure, and then you put it in an email and you email it to somebody in the Far East to program. So what we're looking at here is to bring to your attention the things you need to look at when it comes to secure manufacturing, the things you can do and what services are available out there to help you with that. So we're looking at secure provisioning. So how does my really cool root of trust that I develop actually get onto the bare metal? Is that going to be a secure process? Avoid key leakage. So you're going to use all these private keys buzzing around. Are you going to make sure they are not going to get into the wrong hands? Protecting product identities against overproduction. That's a killer. You're not going to have a second line running in the dark behind the line you're using, producing similar products overnight. So things you need to do to prevent that. And then, of course, the key one is basically to stop your software IP being protected. You've invested a lot of money in this software, so you need to protect it. And then after sales, so the IoT product's in the field, it's being consumed, and we need to make sure, as you heard in the keynotes, that software updates can be utilized. It's one of the key things with security. You must allow this IoT product to be updated, no matter the lowest cost one that you have. Try and at least get some sort of update policy in there. Then we're looking at system integrity, and of course, as we've seen in the keynote, protecting the customer data. So I want to talk quick slide here about trust anchors. There are two types of trust anchors. There's the one that's associated with certificates and PKI. You may be familiar with these. These are the ones that are sitting in your browsers, and they kind of give trust through a certificate. So the browser knows that it can trust that certificate and use that to authenticate. The one I want to talk about is the hardware version of a root of trust. So this is something inside the microcontroller that cannot be changed. And it's basically the ultimate trust point in the whole system. And that's what we call the root of trust. And I'll talk about how you can actually develop that. So, requirements that must be addressed in order to establish the root of trust. So, we're going to go on about root of trust a lot. They're very important. We must make sure that they are robust, and these are the things that you must ensure. So, unique product keys. Ideally, you want a unique pair of keys to be associated with this root of trust. Unique product identity. Most of you are familiar with microcontrollers. They all have some sort of silicon ID. Ideally, you want to associate that with your keys. So giving it unique identity, and then the product with the unique identity can then authenticate itself, and that's very important. You want the device to prove who it is that's sitting there on the end of the connection asking for a software update. Are you actually sending it to the right guy? And then platform integrity. Very important part of that is an immutable bootloader. So this is where you want that microcontroller to be booted into some sort of boot manager in a known way that cannot be attacked from the side through some JTAG port or however other means. It must be immutable. So we'll talk a little bit about that. Identity, very important. So the key to everything is that your IoT product must have a unique identity. It's crucial. Why? Well, it's part of trust. You can instill trust in the device because it can then communicate. If you know what you're communicating with, it can communicate securely. Privacy, so because of that, it can do communications that can be encrypted because you know the identity of the device you're talking to. Safety, of course, you can prevent malicious attacks against the IoT product, as we saw in the keynote, very important. We've seen some of the issues with medical devices being hacked. And of course, eventually integrity. So these are the key things about identity that we must have in our IoT product. So digging down a little deeper now, so we talked about the root of trust. So how do we actually implement this in the actual hardware itself? So you're going to, as designers, you want to go out there and see what microcontrollers are available. You know now what you need to implement, some sort of root of trust. So what do I need to look for in my microcontroller that I'm going to use? So here's some 3 important requirements that you should look into. So you need some sort of secure chain of trust to a boot manager. So ideally you want this device to come out of reset, jump into some sort of ideally ROM-based code, a bootloader, that actually executes, and it does some verification, some identification, checks other software that's in there, signatures, checks for authentication. And that must be a mutable path. So that's the one thing you must look at. The other is the ability to program and lock a section of boot flash memory so that it is immutable. So ideally you want to be able to put some other software in there, maybe say a secondary bootloader, that you can lock off and make sure that the end application cannot access that part of memory. And a small isolated memory area for holding secure keys as well. So this is where you will hold the private keys, maybe the private key pair that you've created for the identity of this product. You want to be able to hold those in a secure area where, again, the application cannot access the keys. But you do want the keys to be accessible by some sort of security boot manager because that will provide services to the application to maybe sign things or check the authenticity of software that may be downloaded. So an immutable boot, the ability to program and lock a section of memory, very important, so you can provision the initial program into the device, and then a small area where you can hold keys that can be managed by the secure boot manager. So those are the 3 things, as a minimum, you really need to look at if you're looking at a microcontroller for your IoT application. So a little bit about the immutable bootloader. So this is from your reset on the device, it boots up and it should jump to ideally, as I said, a ROM bit of code that executes, maybe configures the device to boot up, checks, sets up the clocks, etc., to get it up and running in a stable state. And ideally, it then checks firmware that's on the product in the flash area, does some verifications, checks a hash or some signing of that bit of software before it actually jumps to it. So a very important part of the system. Each loader verifies then the next stage. So oftentimes you'll see this ROM code, it'll be provisioned so that it will actually look at the next stage of bootloader that it wants to execute, check the signature on it, make sure it's definitely okay, been verified, signed by the correct entity, the owner, and then it will jump to it. And then that next software may do may do the similar sort of thing to the application software. So as I said here, sometimes you'll have a first stage bootloader, which will be the ROM version in the device, and then it may jump to a second stage bootloader, which is maybe a more sophisticated manager. So these early ROM-based ones are fairly simple in most cases today. As I said, they just check a hash. So you may want to boot to another more sophisticated boot manager, which can handle updates, handling of keys, etc. So, as I said, a secure boot manager is a little bit more of a sophisticated kind of entity, a bit of software that's running in the device. It generally can handle all the security things you need, like using the keys. So one of the things it can do is check the integrity of itself. It's kind of ideal. Make sure before you boot up that you're real and you haven't been tampered with. That's often a first check. It does a quick integrity check of itself. And then it may look at its secure area. So I mentioned this secure memory area that's got to be secure and can only be accessed by the application. One of the first things the secure boot manager will do will check that area, do some checking to make sure that it's not been tampered with and everything is kosher. Verify the integrity of the application signatures prior to running. So before it actually jumps to the user's application, again, it does a check on that, signature checking, verification, etc. Check for pending application updates. So if a firmware update has come in, that must be managed by the secure boot manager. So generally what will happen, it'll just be flashed, a blob of information will be flashed into memory. The boot manager will be reset. It will check that area to see if a new update is available. If there is, it will then check its integrity, make sure it's been signed correctly, and it is applicable to its actual application. Manage a stable shutdown procedure, also very important. One way of sometimes getting into these boot managers is to keep toggling the reset of the power to see if you can get some kind of access to the software. And then the boot manager, as I said before, does have a lot of APIs to actually help you use the keys that have been implemented. So again, with having a root of trust, the device often has to authenticate itself. And that will require API calls to the boot manager to give you access to the keys, or the boot manager will actually provide authentication. Obviously, the application can't actually see the keys, but it can request services that use those keys. Now, one thing that's really encouraging these days, and we're finding a lot, and you'll see a lot of this coming out early next year, is the semiconductor vendors are seeing the importance of security. So they are embedding more and more security elements inside their actual silicon, which is great news for us in the security industry. So I've just got some examples here of the different technologies. So I'm sure you've heard of the PSA from ARM. These are some other secure enclaves and security type accelerators available in some of the semiconductor devices today. So I've got a few examples down here which show you some of the some are more sophisticated than others, but the great thing is that the semiconductor industry is seeing the importance of security and are starting to embed it in the bare metal. And the closer we can get to the bare metal of implementing security features, the better. So once we've actually devised some way of giving identity to the actual end product, we can then start linking that identity to a chain of trust and create a certificate chain. So down here we'll have a device certificate. This will hold your public key of the cryptographic key pair, and this will be linked to other certificates moving up the chain. So here the root of trust allows us to take advantage of PKI. The chain of trust can be created using a two-stage PK or three-stage. It depends on the OEM. And oftentimes the root certificate authority, it can actually be the OEM. You don't necessarily have to go to some third-party certificate authority. Oftentimes the OEM will do that. Then you'll have your intermediate certificate, because you obviously don't want to expose your root certificate too often to create your device certificates. Each device gets an individual device certificate. That's very important. So you'd basically take part of the provisioning process is to take the identity of the silicon that's on its ID and incorporate that into this device certificate. So the certificate, which is holding this public key, which links you to the PKI, is very strongly tied to the actual die that it's sitting on. Again, keeping that all locked. So, looking at the development as a summary here, so the creation of the trust anchor is critical. You must get that trust anchor inside the microcontroller device key. And the great thing is that microcontroller architectures are progressing quite rapidly, in fact, to give you more and more features to allow you to embed this root of trust. Here are some secure MCUs that are coming out. As it says here, Microchip, Renesas, all of the top guys creating secure MCUs with very, very robust security features embedded. So the trust anchor allows you, the RT product, to utilize the PKI. The PKI is really where you want to go, and that's what allows you to do that once you've got your trust anchor. You can then create a chain from it. So as I said before, so you've spent a lot of development time. You've got these nice, cool software tools that allow you to easily create a root of trust. You can create these certificates, and you've got your PKI. Everything's really great. You've finished your applications, all tested really good. Everything's great. Now I'm going to email it to somebody to mass produce it. So let's look at how we can make sure that your software is safe. And one of the things we really try to promote is that you have this zero trust philosophy. So every aspect of your development cycle, you should question, well, who's going to see this? How can I make sure that this isn't going to go off somewhere else? How do I know that my keys are going to be secure? These are the kind of things you need to look at all stages of the manufacturing process, even inside your own company. Who is actually seeing this software? Can they be trusted? So one of the things you will first do is actually program, or what we call provision, your trust anchor, your root of trust, into that MCU device. So obviously a critical step. So we call that provisioning. So this is where you take the empty device from the semiconductor manufacturer. It has all this wonderful security stuff on board, but of course it needs to be programmed with your keys and your certificates that we've just discussed to implement your chain of trust. So provisioning is the process of establishing this root of trust by programming your MCU. The provisioning process is usually undertaken by some sort of programming center or a contract manufacturer. So that should immediately start ringing alarm bells. So a lot of OEMs these days choose to do this in their own security areas to make sure that it's secure. So as it said, it's important that a secure programming center is used in all cases where you program in the private keys into the device. So this provisioning is a very important step. So one of the ways you can make sure that the provisioning process is secure is by using one of these secure provisioning or programming centers. And they're available today from some common distributors that are out there in the market. So in order to securely provision the device, this is sending your software out to actually embed your keys. One of the things you can take advantage of is a hardware security module. So this is a secure module that is able to manage encryption and secure information. And these ideally should be mounted inside the programmers of your devices as close to the programming head as possible. And what the HSM allows you to do, it allows you to securely transport all this provisioning information, your keys and your firmware, into the HSM. Because, of course, what you can do is you can take the certificate from this HSM, and, of course, therefore the public key, and you can use that public key to encrypt the information that you actually want to send to the programming head. So basically using this process allows you to take that wonderful, secure root of trust development that you've carried out. You can wrap it using the actual targeted programmer you're going to send it to and securely transport it to. So only this HSM inside this programming head can expose that. One of the great things is, as I said, with these semiconductor manufacturers, they are now providing bare metal capabilities whereby the keys are actually a part of the semiconductor device itself. So in some cases, you will be talking to it and provision it using the JTAG or SWD interface. In the new microprocessors, the keys are actually in the bare metal. This allows you to extract the device certificate and provision the device over an encrypted communication path, which is great. Mastering, so this is where you actually take your final application that you've tested and it's ready to go, and you package it inside an encrypted blob, ready to be transported wherever it is. Could be in the field, it's in the customer's site, be sent over the air, or another programming facility. So this is where you actually finalize your software, mastering it. What you do here is you assign the software. So once you've actually put it into a blob, you actually can encrypt it with a ephemeral session key because it's a large amount of data. And this allows you to then be able to securely transport it to wherever it is going to be programmed. Again, with the remote mastering, you take advantage of this HSM. Using the public key of the HSM, you can transport the image, this software, to a secure facility for programming. That's to the HSM. Finally, what you can do on the device itself, so this is, say, where the device is inside your IoT product itself. That blob can be actually transported into the device itself if it's sitting on your IoT product. Into the actual microcontroller. Because what you can do, again, you can facilitate the private-public key pair in the device itself, extract the certificate from the device, and therefore send the information to the device in an encrypted manner, again, secure. Then what generally happens is the secure MCU has its secure boot manager, which you previously provisioned into it. It will then see that there is an update block appeared in its memory. Of course, it's all encrypted. It will check it, that it's been sent by the correct person, the OEM, correct owner, check its integrity, and also check to see if this update is actually for itself. Is this actually referring to me? It will check it against some sort of policy. If it's happy with it, it will then unwrap it, flash it into the device, and none of it has actually been exposed to the outside world. It's been encrypted all the way through. So one of the things that's really encouraging in the industry, we talk about security a lot. We're all here today, and we've seen a lot of bad press in the news. But the great thing is that the semiconductor guys are seeing this as an opportunity, and they're racing to be the best secure devices that are out there. So you're seeing much more secure devices coming out with separate secure enclaves inside the device, private public keys already provisioned into the device as it leaves their factory, and all sorts of other features that allow us to easily embed security into our IoT products. So that is a great positive that we're seeing currently. MCUs with immutable boot and secure memory enable a chain of trust. So if you are designing an IoT product, make sure that you've got this immutable boot. It's very important. Not all microcontrollers have them. Make sure it's got a good immutable boot. Implement a PKI, so you can implement your chain of trust. So you can check and verify each component in the chain. And we do promote this zero trust. Question everything. Who is seeing my software? Where are those keys going? Who is creating those keys? And if you take that philosophy and have a time to just sit down and think about it, where you're sending your keys, where you're sending your software, it's going to help in your secure development. So hopefully I've emphasized the two key points I want to cover today, which was this chain of trust and your root of trust. You've got to think about that trust anchor. You make sure that it's solid in your MCU and finally your IoT product, and then looking at protecting your software as it's going through the development chain. Any questions? Yes, sir.